Hi, everybody. I'm Denny Dahl from INQ, and this is the description of the third problem for the Q Center Challenge competition for 2025. In this challenge, we'll analyze a small four-city traveling salesman problem using two different encoding schemes and simulate their behavior using QAOA, which stands for Quantum Approximate Optimization Algorithm. The TSP or traveling salesman problem is a well-known combinatorial optimization problem, which is NP hard. Intuitively, this means that as the problem scales up in size, solving it exactly on a classical computer rapidly becomes harder. Solving the problem means finding a particular tour which visits each city one time and comes back to the starting point. We are trying to find the tour that has the shortest total length of all the tours. Scaling the problem up means adding more cities. There are powerful classical heuristics which find very good tours for large numbers of cities, even into the tens of thousands. From that vantage point, the problem we will analyze is quite small. In the first encoding scheme, we associate a single variable to each of the six legs, connecting a pair of cities. That's why we call this scheme leg variable encoding. The advantage of this scheme is that it's easy to write the total distance that is taken by a tour. You can see the formula for that on this slide. There is a counterbalancing difficulty with this formulation. Not all settings of the leg variables are valid. We address this issue using constraints, which we must encode as penalty functions in the objective. This is the first part of the challenge. One difficulty with handling the constraints is that we generally do not know in advance how strong to make the constraints. In fact, we can scale up and down the strength of the penalty function, which captures the constraints. Finding the smallest scaling parameter which results in a well-posed problem is our first task. The second encoding scheme uses a switch network to parameterize the different tours. There are many switch networks with different properties. This slide describes a sorting network, but in our exercise, we will use a slightly different network. There's an advantage to this encoding scheme. All settings of the switches give rise to valid tours. This means we do not need to implement any constraints, and so we do not have to add a penalty function to our objective. The drawback of this approach is that the objective has higher order terms. Fortunately, there are straightforward ways to handle that when we construct our circuit. One important point to note, since all settings of the switches in the switch network yield valid solutions, this means that a given valid solution is generally encoded in multiple ways. That's certainly true for this problem. Finding out how many different switch settings give rise to each solution is one of the exercises for part 2. In the last part of the challenge, we construct QAOA circuits for both the leg encoding and the switch variable encoding. By varying the number of layers, or P, in the network, and the functions giving the beta and gamma parameters for each layer, the total amount of probability that is steered into the ground state will change. Your goal is to maximize the amount of probability in the ground state by changing the dependence of beta and gamma on the layer. By restricting the functional form of beta and gamma to be linear functions of the layer index I, the space of parameters is much smaller. This restriction is consistent with thinking of QAOA as an approximation to the adiabatic algorithm, in which we slowly transform a Hamiltonian from a simple one to a complicated one. We initialize the qubit register to the ground state of a simple Hamiltonian. As the Hamiltonian gradually changes, the state of the qubit register closely approximates the instantaneous ground state of a time-independent Hamiltonian, which is frozen between its initial and final form. Good luck. Here's my email address. Please reach out if you have questions, and I'm looking forward to getting your responses.